again, your textbook and a lot of reference materials are on the rational reasoning site. So if you go to rationalreasoning.net, you can click into the book section or you can click into the homework section, the iMath section. And make sure you don't forget about the book. There's a whole textbook in here. We've been working in Module 2, and if you click on this, the top link there is text, which it's fairly readable as a text. There's lots of words, but it's not overly mathy, if you know what I mean. It's not just like a whole bunch of diagrams with no words to go along with it. So I hope it kind of makes sense. Now let me get this to go bigger. There we go. So the main topics from this chapter, as you can see here, this is just Module 2, Chapter 2, whatever you want to call it. Quantities and covariations of quantities. That was just talking about quantities are the measurable items of things we like, the distance from the front door in feet, or the height of the water in the tank measured in meters, whatever it might be. Those sorts of quantities and the units of measure for them, and ones that change over time that we can maybe use variables to express. That was the beginning of where we went. We talked about constant rate of change a little bit while I was here, and then you should have talked about this last week with either Mr. Ward or Mr. Brownstein. But we'll talk about more with constant rate of change in linear functions today, because I want to make sure I want to make sure you've got that down, because that's one of the key relationships that sets up how all of calculus works. Which sounds weird, because like I said, it's really just about linear equations and constant rate of change, but in calculus, instead of having one constant rate of change forever, you just think like, well, every little tiny piece has its own constant rate of change, and if you make the pieces tiny enough, no matter what sort of function you have, as long as it's relatively smooth, doesn't have weird asymptotes, as long as you're not talking about those sorts of weird spots in a function, anything can be described in terms of constant rate of change relationships over little tiny sections. So in any case, we'll talk about constant rate of change more today. And then, like I said, the average speed, average distance, or average speed or average rate of change, and the distance formula stuff, I think most of you got that sorted out in the forums, and you did really well on the homework on those once you got going. So we'll talk a little bit about those and then more about absolute value today. So those are the 7 different sections here of the chapter. And again, if you want to look at this the textbook, it's under under the rational reasoning section, not the homework section. Under these modules, this is module 2. The top option is the text. We're actually going to come back and I'm going to use one of these PowerPoints because it's got some cool diagrams in it. I didn't want to recreate for some of our absolute value stuff. But there's PowerPoints in. You guys have access to the PowerPoints, correct? Okay, because I only have the instructor version of this. I know in these parts down here, these are the investigations that I have slightly other stuff. It just has comments for teacher, but I just want to make sure you still had access to the PowerPoints. Those are pretty useful in terms of it steps you through and then gives you some additional examples if you're looking for examples on things. And just to pull this up real quick, they're really long. Like if you look at this, it's like 100 and something slides long, but these are all clickable. So if you want to go to stuff about absolute value inequalities, click on that and it'll skip down to where that is, which is like slide 84. There's a lot of information in there, and it's something that you can go through on your own. It teaches you through it. It's not just like here's a question and it doesn't give you an answer, like it's just a teacher posing questions. It has the questions and the answers and diagrams and figures where necessary to kind of demonstrate how to solve these problems. And this is what we're going to do on here today, absolute value inequalities. And we'll start with that. But in iMath, so there's a lot of, these are split up into by section, so it seems like there's a lot of stuff, but the reason I have it that way is so you don't have assignments that you just keep scrolling. So they're all split up by what section they're related to. So I know it looks like a lot of things, but I wanted to kind of keep it compartmentalized so you can see like, oh, so this one's about 2.7. If I'm not ready for 2.7 yet, I'll do the 2.6 and then I'll go back and review the 2.7 stuff. But the homework on those is due tonight. These are the not quite so wordy and just a few questions sorts of pieces, as opposed to the lessons, which are wordy and kind of talk you through. In upcoming sections, I might not assign the lessons for everything. I assigned the lessons for all of it since I wasn't here. And I wanted to make sure that you kind of got the idea of where this material is and how to read it. So you won't have the lesson and homework for every single section. It kind of depends on the section. But I know I did assign all of them while I was gone, just so you'd have some extra kind of that wordiness or descriptive piece to that. So again, I apologize, I was out sick. I haven't been sick in like a dozen years. Happens sometimes. But in any case, on here, let's see, what did I want to say about the homework? Oh, I know, the forums. If you have a question and you want to ask in the forum, please don't just like post the question and leave it blank or say, I don't know how to do this. If you have a question you're struggling with, like maybe you've done parts A and B and you're stuck on C, maybe say like, okay, so I got A and B, but I don't know how this relates to C, or I don't see what's supposed to happen next, that's okay. But if you have something that you've tried, like I was trying to subtract these two parts and divide it, but it's not coming out right. What am I doing wrong? You can get more useful answers if you give more input into what you list in the forum questions, as opposed to just post the question with nothing, in which case I don't necessarily even know which part of a 5-part question you might be stuck on. Or if you just say it's part C, it's like, well, what about part C? Did you get A and B? Did you try anything yet? If you have tried something, I know it takes a little bit more time, but if you have tried something, that'll help me, anybody else, like answer the question in a way that will help you not just answer that one, but understand what the concept is, so that like we can figure out where it is that it got confusing, if that makes any sense. All right, so constant rate of change. So I want to go over a little bit more with constant rate of change than, let's see, where is it? Oh, here it is. Than maybe you did in class, just because I think this is such a key topic here. This is actually adapted from some materials. It's little pieces of some materials that I use with my Math 270 class, Calculus 1. But it's the same material. It's just extremely important. So constant rate of change is something, the word sounds fancy, but it's something that the concept of we use all the time. So if you're driving in your car, once you get on the highway, you set the cruise control to 70 miles an hour. That 70 miles per hour, that's a constant rate of change or a constant speed. What does that mean? Like, how could you interpret what that means? Like, what does it mean to be going at 70 miles an hour? What could you conclude from that? Anyone? Yeah.
For every hour you will travel 70 miles.
Yeah, for every hour you travel 70 miles. So, do you have to travel a whole hour before you could say that you are going 70 miles an hour? No, otherwise no cop would ever be able to pull you over, right? They have to wait a whole hour to figure out if you're going 85 miles an hour. That's not quite how it works. So we can say that, and that's certainly true, but that's not the only thing. And so if we want to give a more descriptive meaning, we can talk about any amount of change. So, because, like if I were to travel for 2 hours, I know I'd go 140 miles, right? If I were going at 70 miles an hour for 2 straight hours, which is kind of hard to manage. But I don't even have to go a whole hour. I could go parts of hours. What about in half an hour? If I were going 70 miles an hour in half an hour, how far would I go? 35 miles, right. What about in a tenth of an hour? 7 miles, and like, a tenth of an hour, what is that? That's like 6 minutes. Okay, I could probably go on cruise control for 6 minutes without having to break that, so it seems a reasonable something I could compute. And I could go on and on. We could list any number of hours, any amount of time measured in hours, and come up with how many miles I would travel, and I could convert that to something other than miles. If it was like 0.07 miles, I might want to say that in smaller units, just like 1/10 of an hour is kind of weird. I might want to say that in minutes. We can convert them, of course, but for any amount of time traveled, any amount of elapsed time, the distance that I travel is going to increase by 70 times that. So the units aren't the same units. I've got time measured in this particular case, time measured in hours and distance measured in miles. This miles per hour bridges that. So for any amount of additional time that I travel, multiply it by 70, that tells me how many extra miles I've traveled. And that's a more extensive view of what 70 miles per hour is. And that's not just for average or this constant speed, but it's for any constant rate of change relationship, slope. If you're thinking y equals mx plus b, if you know m, you can figure out a change in x of any size, how much change in y is associated with that. But again, so this, for any time traveled in hours, multiply by 70 and you get the distance traveled during that time in miles, which sounds kind of, like I said, it sounds kind of like, well, yeah, I know that. We have to make sure, remember to use that all the time. So, quick example, not 70 miles an hour, but a different rate that isn't to do with time and distance here. You're filling up your gas tank, gas is $2 per gallon. So what does that mean? That's a constant rate, a constant unit price in this case. There's lots of different words that go with constant rate of change. We could talk about speeds, we could talk about prices, but it's not, it's not just a fixed price, it's a unit price, price per something. But the meaning of this $2 per gallon, well, if I'm thinking about filling up my tank at the gas pump, I wish it was $2 a gallon. It's not. But if this were the price, every time I get an extra gallon, it costs $2 more, right? But more than that, for any extra number of gallons, however many it is, whole number, fraction number, probably decimals on the gas pump, whatever it is, if I multiply by 2, I get how many dollars those extra gallons of gas cost. Whether it's a increase of an extra 0.7 gallons or an increase of 14.8 gallons or whatever it is, multiply by 2, and I get the extra cost associated with them, right? So it's that same, whether it's distance and time or some other sort of rate, we have the same relationship for any additional, in this case, gas purchase measured in gallons. The extra cost is 2 times as much when it's $2 per gallon. More like 4 these days, I think. But in any case, let's do a problem here. So not just gas, but we've got another price situation, more interesting price. Store sells make your own snack mix gifts. The box that it comes in is $B. Snack mix is $2.75 a pound. Oh, $2.75 a pound, that's like that $2 per gallon. That means for any additional amount of snack mix I put into my gift, it'll increase the price by 2.75 times as much, right? An extra half a pound would be half of $2.75 added onto whatever price I had before. So let's think about the symbols here. I'm going to use, on this one, let's say we've got this X, so that we're doing this the same direction. We could set it up either way. Let's say that X is the number of pounds of snack mix in this gift. So what would Y be? What's the other thing that we're measuring besides the number of pounds of snack mix? Yeah, cost, right? So if X is the total number of pounds, then Y would be the total cost, right? In dollars. Good. Yeah, and make sure, when one of the things that is easy to make a confusing problem out of is by not talking about your units of measure or not be specific about how you're describing something, which makes it hard, like this situation may be hard to make a mistake about what you mean. But let's say I was talking about a tank of water and how much water was in it, how much space is in it. I might want to like, okay, how many feet of water measured from the bottom, or how many gallons of water, or how far it is from the top, or how much is left, how much is drained out. There's lots of different situations with water in a tank that maybe you could be measuring pounds of snack mix, maybe not quite so many options. But here we'd want Y to be, the total cost of a gift that has X pounds of mix in it. So we're going to have Y depending on X, or Y based on knowing X, the price based on knowing how much snack mix you have. So these other symbols, delta X and delta Y, those again we use to talk about the amount of change, not the overall total value, but how much something changes. So delta X then would be about what? What would delta X be? Well, if I know X is the number of pounds of snack mix in a gift, if I said delta X equals 0.4, what would that mean happened if I say delta X is 0.4? Delta's about change.
What's the constant rate of change?
So a constant rate of change would be a delta Y and delta X in a proportion.
They got 0.4 pounds.
Yeah, if I said delta X is 0.4, that means a change of X by 0.4. And since it was a positive number, that would be an increase by 0.4, or putting 0.4 extra pounds of snack mix in. So just a change in the weight, the change in the number of pounds of snack mix, which is how we're changing the weight. Similarly, delta Y, if I know what Y is, delta Y indicates a change in Y. So I could talk about delta Y as being a change in a change in the dollars, a change in the price of this gift. Probably because we put more snack mix in, or took it out. If you're taking it out, just be careful that no one sees you, don't touch it. All right, but M is this constant multiple, this constant proportion between the delta Y and the delta X. In this case, we have a value for M. What's the value for M?
2.75.
Yep, 2.75. It's that $2.75 per pound. So dollars per pound are the units on it. But in terms of the relationship at the top there, it says if I have a change in the weight of snack mix, multiply it by 2.75, and I get the change in the price of my gift that I'm getting that involves snack mix. So, I think I froze this. There we go. So it's that constant rate of change is M, but in this case we have a value for it. We don't have to just call it some unknown. It's not changing. It's 2.75 is the numerical part, and the units are dollars per pound. All right, so suppose we have this scenario then. After scooping some mix into a box, you decide you want more. The additional cost you'll pay for 1.5 more pounds of trail mix is 2.75 times 1.5, and that result would be in dollars. So the additional amount you pay is in dollars, and the number is whatever that multiplication comes out to. So with respect to these three symbols, in this situation here, what's the value that corresponds to delta X?
1.5.
Yeah, 1.5. Delta X is the change in the amount of snack mix measured in pounds. And so that's that 1.5 more pounds. Oops, sorry. Somehow I clicked something weird. Let me get back to where we are. There we go. Delta Y. What about delta Y in this situation?
275.
Not quite.
It's 275 times the change in X.
Delta Y is M times delta X. It's the change in the, concept-wise, it's the change in the price. So it's 275 per pound that we changed it by, So this whole multiplication, that 2.75 times 1.5, whatever that comes out to, that's delta y, because we know m is 2.75. Right, so the constant rate of change is that 2.75, that rate type unit, whether it's miles per hour, dollars per gallon, dollars per pound. Those are our constant rates, or the rate that we're using for all times or all pieces of the situation. And so this 275 applies to however much snack mix we're doing. It's 275 a pound. All right, so suppose I change new scenario instead. I just dumped a bunch. I'm like, that's too much. I'm going to take out 0.4 pounds of the snack mix. If I do that, in this description here, what's the value of delta x? Negative 0.4, right. Remember that x is about the pounds of snack mix. Delta x is about a change in the number of pounds of snack mix. So we're changing it by taking out 0.4, so negative 0.4. It doesn't mean I have negative weight, just means that I have less than I did before. I've decreased the weight by 0.4 pounds. So negative 0.4. And then delta y would be, how would I compute it? You don't have to do the computation.
Could you do 2.75 times
Right, exactly. 2.75 times negative 0.4. So I'm going to get a negative for that also. What if I get a negative dollar value, what does that actually mean? Yeah, cost decrease. I get a negative dollar value for delta y, not for y. Y is the price of something, and I know the price of something isn't going to be negative, but delta y, the change in the price, can be negative. It indicates a decrease in the price, and that makes sense. If I remove weight, if I remove some of the snack mix from it, it should cost less than it would have with all of that in there. But again, m is this 2.75. So just keep in mind the difference between delta x, delta y versus x and y, the main variable values, versus just talking about how much these variables are changing. Those are different things, because in terms of this proportional relationship, x and y may or may not be in proportion to one another. Y may or may not be a multiple of x, even if changes are proportional. In this case, unlike the gas price one, y and x, if I want to know my total price, I multiply it by the number of gallons by 2. If I want to know changes in price, I multiply the changes in the number of gallons by 2. Because there's no other underlying fee, I guess, unless you're using a credit card and they charge you for that or something, some sort of fixed price plus whatever per gallon. This situation, if you have to remember the first page, I do because I wrote it, said something about the cost of the gift basket. The cost of the basket itself is B dollars, or was it the weight of the basket is B pounds? I forget. But it was the cost. But there's this other piece to it that doesn't depend on how much snack mix you have, how much it weighs, or the 275 per pound. It's just there's this basket that costs B dollars or something, and then you add in snack mix that has a certain cost per pound, but the basket doesn't have any cost per, it's just B dollars. So in this case, the total cost of the gift and the change in the cost of the gift aren't related in the same way to x and delta x. It's not, the total price wouldn't just be 275 times the number of pounds. You'd also have to add in the price of the basket. So let's see. This is going to be a more complex example here. Soldier lowers a flag from the top of a pole at 0.75 meters per second. So we're doing some sort of ceremony, lowering this flag at a nice constant rate. That means that during any interval of time during the ceremony, the height of the flag will decrease by 0.75 times the amount of time that's gone by, where we're measuring the height of the flag above the ground in meters, and we're measuring time in seconds. So we have these two different sorts of units, but the rate is in meters per second, so that multiplication there takes care of all the units. So let's say that y is the height of the flag above the ground in meters. Take a minute, see if you can write out descriptions for these. So the y we already have, it's listed right there, so that we're doing this the same way, using x and y the same way. But think about what else we're measuring and what the rest of these might have. Okay, try to write it down, confer with a neighbor, make sure you include units or relative to something. So this is just kind of setting up a situation, and then we're going to answer some numerical questions about this once we have our variables sorted out and our relationships. All right, so let's see, we said y is the height of the flag above the ground in meters. What about x? What's the other quantity we're measuring in this situation?
The interval of elapsed time in seconds.
Yep, the amount of elapsed time in seconds, right. We've got time in seconds that we're measuring, and so it's not like time since noon or anything like that, it's just time since started lowering the flag, if you wanted to talk about that. But yeah, how much time has gone by? So number of seconds since we started lowering the flag, number of seconds elapsed. Y is the height of the flag above the ground measured in meters, not like it's elevation, like relative to elevation 0 or anything like that, just height above the ground. So delta x and delta y, those are their own variables. They're related to x and y, but they are their own thing. What would delta x be talking about? What's the meaning of a delta x for this situation? Yeah.
The change in time in seconds?
Yeah, the change in time in seconds, or an interval of elapsed time. Doesn't matter if it was time 2 through 7, time 1.8 through 9.2, time 0 through something. We can have a delta x, an interval of time measured anywhere while this flag is being lowered. Doesn't really say how long it took, but since it's being lowered pretty slowly, we can just imagine x, this number of seconds, is at least a couple of minutes long, at least like 100 seconds or so. So a change in elapsed time or an interval of elapsed time. What about delta y? Yeah.
It'd be the change in height in meters.
Yeah, change in height of the flag in meters. During, again, you could think of it like during some interval of time, it's how much the flag height changed by. Now, presumably it could go up or down based on how we've used these changes before, but since time generally goes forward, and this says that we're lowering the flag, we'd probably only talk about the flag decreasing in height during this situation, since that's what's going on in reality. But we could talk about like what happened, you know, where was it 3 seconds ago? We could say it was higher than it is now. So it's not that we have to reverse time, but delta y in any case is talking about a change in the height of the flag during some interval of time. But we'd measure that change in meters, and just between two different points in time, we're going to have the flag height change. And it doesn't have to be the beginning, doesn't have to be from the top of the flagpole. It can be measured from any one point to any other point during the ceremony. What about M? What's M here? What's the value of it? This rate of change, yeah.
Negative 0.75 meters per second.
Good, yeah, negative 0.75 meters per second. So changes can be positive or negative. The other examples we talked about were positive rates of change, and we had, what do we have, like $2.75 per pound. If you have more pounds, you have more price. $2 per gallon. If you have more gas, you have more dollars, more higher price. And I forget what the first one even was. 70 miles per hour. More time goes by, you're going to have more miles that you've traveled. But in this case, as more time goes by, we have a lower amount of height. There's a negative rate, a negative ratio between those amounts of changes. When one gets larger, the other gets smaller between the x and the y. So this m is going to be something negative here. It's negative 0.75, and the units are meters per second. So it's a constant rate of change. That's what's meant by m. But it's, in this case, the key part that I wanted to point out is that it is negative. Those can be negative or positive. It's not just the size of the change, but it's also the direction of the change. That's important. Delta y and delta x can have negative values also. But in this case, whatever a corresponding amount of delta y and delta x, change in time and change in flag height are, if you put those two in proportion to one another, one's going to be getting larger as the other gets smaller. So you're going to get a negative fraction for this m if you do delta y divided by delta x to compute it. Or in this case, you can just say, oh, it's lowering by or decreasing by 0.75 meters per second. All right, so same situation, m value given previously, lowering by 0.75 meters per second. How much does the height vary? How much does the height change between 4 seconds and 6.9 seconds since the flag left the top of the pole? Well, we could do a computation for that, but what is the computation we would need to do? And it might help to think of these. This is just talking about how much change is there. So let's see, delta x. What was the x in this situation, the time or the height? Time, right? So if I want to know in this situation, what's delta x, that's looking for how much change in time have we had. What computation would we do?
6.9 minus 4.
Yeah, 6.9 minus 4. We want to know final minus initial, right? How much time has gone by? Now, maybe that's easy enough to just compute it. How much time is that that's gone by? 2.9 seconds. Yes, 2.9 seconds. So delta x, we could say is 2.9 seconds. Delta y, not so easy to maybe not as easy to do in your head. M though, we know the value for m, right? M is that negative 0.75, this is on the previous slide, same situation. So negative 0.75 meters per second, and we have a number of seconds, so we should be able to get the value for delta y. Here, let me just write this up here, because it's not on every page here. Delta y is m delta x. And if we know this, and we know that, we can certainly get that delta y, right? Now I don't need you to do the multiplication, but we would just need negative 0.75 times 2.9, right? Whatever that comes out to, it's going to be something negative, which would indicate delta y, the change in the height of the flag, is something negative, meaning the height is less at the end of the interval than at the beginning. That should make sense, right? Whatever it is, like 2-ish meters, it's gonna be about 2 meters less. Now, this delta y equals m delta x. Changes in x are proportional to changes in y. If we know how much one of the two variables increases or decreases, then we should be able to figure out how much the other one does if we know m. Or if you know those two amounts of change, you can put them in proportion, divide them to find m. So this is part of what we've been doing, and this is what we've done so far. We're going to go back to the flag problem in a second and do something else. The other piece to what you've been doing, instead of just describing the changes, we can also find total values. Like if I told you how high the flag started, we should be able to figure out how high it is later, not just how much lower it is than when it started, but we should be able to find the final height. Or with the gift box situation, if I told you how much B is, the cost of the basket itself, you would have been able to find the total price of the basket once we knew how much we were increasing or decreasing things. But we can find these total values, actual values of y, generally is what we're interested in, the output. It's what we have to compute. And those are related in a variety of different ways, depending on what information. But if you want to know like a final y value, the value after something has happened, if you have a starting point, you can add or subtract on the change. So for instance, with the flag question, which we'll get back to in a second, if I know the starting height and I know how much it decreased in height, I can find the new height, the final height, right? Just by y initial and then subtract that delta y. It would be, well, add delta y, which would be a negative number in the case of the flag since it was only going downward. So if I want to know new y values, not just delta y, delta x sorts of things, then I have to know an initial y value and how much I changed from that. But keep in mind that that delta y is m delta x. Delta y is m delta x. So I could write that expression as y final equals y initial plus delta y. Looks like mystery math. It's like, oh, well, that's the same as y final equals y initial plus m delta x, or maybe that looks or starts to look maybe a little bit more familiar. To find delta x, x final minus x initial, this is this point slope form for an equation. Maybe you don't have final in there, maybe you just have x's and y's. But if you have a starting point, and let me write this down here. And I'll just write it y, final y or whatever y you want. If you have some place to start, and then you change it by some certain amount away from an initial value of x, this equation should look familiar as like point slope form, which is pretty simple to, like if you have information, like I said, there's computations we can do, but I want you to think of like the structure of what we're doing or what the computation is as opposed to like punch it in a calculator and get a decimal value for whatever. But if I have some change in my x coordinate, x final minus x initial, or in general, some generic x in the future, and an initial x value, this is calculating my delta x. So m delta x, this calculates change in y altogether. And if I know how much y changes by, and I add it to some starting value for y, then I have a final value for y. So starting value for y plus a change in y, m delta x, or m times x final minus x initial, tacked on to that initial value of y gives me a final value of y. Or, as I wrote here just without the final on there, for a general value of x that you can plug anything you want into later, x minus some specific starting point gives you something like your delta x. You can multiply by m to get delta y, tack that on to an initial value of y to get a final value of y. whether it's a positive number or a negative number. So these pieces all go together. Here they are at the top again. So let's go back to this flag and answer some questions. Not necessarily do the computation, but write out a computation we'd need. So let's say, to put some specifics in this, let's say the flag started at 110 meters above the ground. That's where it is when he starts lowering it. How would I find out how much the flag lowered after 3.72 seconds has gone by? Is this asking about, let's see, how much has it lowered? Is it asking about x, delta x, y, or delta y? It's not asking about m, it's not asking for rate. So I know it's one of those four. Which is this asking us to find of those four quantities that we can measure? How much has it lowered after 3.72 seconds? Yeah, it's asking for a change in y. Oh, so orienting ourselves to the problem, I know I'm trying to find change in y, delta y. Delta y is m delta x. So do I know these two? Yep. My m was given, it's listed in a sentence, so it's really negative 0.75. And delta x, how much time has gone by? 3.72 seconds. And this happens to be, 3.72 seconds, the way it's worded, it kind of indicates it's from the beginning. But any 3.72 second interval would be the same. I do negative 0.75 times 3.72, and I would get that delta y. Good, so yeah, this part A is asking for a delta y value. How much did the height change of the flag? What about B? What is its height after 12.87 seconds have elapsed? Which quantity is this asking for? X, delta x, y, or delta y?
Y.
Yeah, what is its height? Not how much did the height change, but just what is its height? It's looking for a value of y, the height of the flag. So if I need to find y, I need to know where it started and how it changed from there. I have this written in the shorter format up there. Y initial plus delta y. I need to know y final, a y value. Do I have an initial value for y? Y initial plus delta y? Started at 110. And then to find delta y, we just found a delta y in the last problem. It was negative 0.75 times, a different number of seconds there than what I want here. But for this one, y initial plus delta y would be 110 plus, let's see, this after 12.87 seconds have elapsed. So that's a delta x, right? So I know my m and my delta x. All I'd have to do is add those onto, well, it would be a negative number, but add that onto 110, right? So 110 minus 0.75 times 12.87. That would give me a new height. If I just do the 0.75 times 12.87, that's how much the height's changing, and that's going down. You can do these kind of, think your way through. You don't have to memorize a formula. You can say, all right, so in 12.87 seconds, the height would change by 0.75 times that amount, like 9 point something, 10 point something meters. And it's going down. It's really a negative 0.75. And then I could subtract that 10-ish meters from the 110. So I get something around like 100 meters or 101 meters. I don't actually know what the computation is exactly, but is that okay on this one? All right, so notice what we're doing. When you're reading this problem, it's asking you to find some values in this constant rate of change relationship here. Make sure you think about what it is you're being asked for. The first question, part A, was asking for a change in the height only. The second question, part B, was asking for what's the new height. So it's asking for a value of y. So a delta y question versus a y question. And the finding a y value is more complex because you have to know where you started and how you change, not just the change. All right, so if I wanted to describe the flag's height after x seconds for any time x in the ceremony, this is asking for a formula for y, just with x, not a specific number. But if you know how to do this for a specific number of x into the ceremony after x seconds have elapsed, so just like these two, a lot of times we are concerned with how much it's changed from the beginning, from time 0. And that's why a lot of times when you're writing equations, you kind of have the y-intercept, the b is your given, but I've got x seconds have gone by, so what's my new flag height? Oh, well if x seconds have gone by, then delta x is just x, which is kind of repurposing that x. But if x seconds have gone by, then my change in time is x. And this is negative 0.75, so my delta y would be negative 0.75x. That makes sense? So after x seconds have gone by, my flag's height's decreased by 0.75 times however many seconds that is, 0.75x. Decreased by meaning subtract 0.75x. But if I want to find what the new height is, I have to start it from someplace, and it's not 0. To find the height y after any number of seconds x have elapsed, I start at 110, and then I decrease by 0.75 meters for every second. So that's 110 minus 0.75x. Right? So starting point and change away from that. So just one last example with this, with another kink thrown into the system. More flag stuff, just because easy enough to change up. So we're trying to do this ceremony, but it's windy and the chain was tangled, so it took a little bit to get going. But 20 seconds into trying, everything's going, and we have the flag going down at its nice ceremonial even pace, at its nice constant rate of change. So we're wiggling it around a little bit, so it's not all the way up at 110 at time 20. It's at height 104 at time x equals 20 seconds into this ceremony. Weren't quite able to do it evenly, it was a little bit caught. But if the flag was at 104 feet above the ground at x equals 20, the time when we were able to begin this nice ceremonial, even, constant rate of descent, if I want to know how much would it descend in the next 3.72 seconds, is this question asking about x, delta x, y, or delta y? Which one is it asking us to find?
Delta y.
Yeah, delta y. Delta y is not too hard. Delta y is m delta x. I know m, negative 0.75, since we've gotten the chain untangled. And what's delta x? 3.72. This doesn't mean we're 3.72 seconds into the ceremony. It's the next 3.72 seconds, but it doesn't matter. This is during this time when it's lowering at this rate. For 3.72 seconds, we're lowering it at this 0.75 meters per second rate. So how much would it descend? Negative 0.75 times 3.72. Right? That's it. We don't need to know that it was 104 meters above the ground or 20 seconds to answer this question. It just wants that delta y. Now, question B, what would the flag's height by this time be? There we go. That is at 23.72 seconds into the ceremony, which that's almost kind of extra information, but I know where the flag was at time 20. At time 20, I know it was 104 meters high. And then according to part A, I know how to find how much it lowered, how much lower it was in the next 3.72 seconds. So for part B, I just have to do a little quick computation using part A, right? Part A tells me how much lower it got, delta y. Negative 0.75 times 3.72. How much lower than what? How much lower than 104? So 104 minus 0.75 times 3.72. So it'll be right around 100. I don't know the exact number. It'll be something less than 104, but certainly not 23.72 times 0.75, right? Because this constant rate of change only really started working at time 20. So by time 23.72, we're only using it for that 3.72 seconds. So we still actually have the same delta x for part B as we did for part A in terms of how long we've been able to use our constant rate of change. All right, so one long question here. What would be the flag's height at 45.31 seconds into the ceremony? Take a minute. You don't have to do the computations here. You don't have to grab a calculator, but write out what arithmetic would need to be done to answer this question. Think about it again. What's x, delta x, y, delta y, and what are we looking for here? All right, so question. Overall, what variable value are we trying to find to answer this question? X, delta x, y, or delta y? Y. Yeah, we're looking for a height. But in order to find the height, we're going to need to know starting height and a change in the height. All right, so what was the starting height, y initial, that's important here?
104.
Yeah, 104. So at 104, that's at time 20 and height 104, that's when this constant rate of change situation started. Prior to that, all sorts of whatever. So height of the flag over time was probably apparently 110 according to the last question, and who knows what happened during that first 20 seconds. It was a bit of a mess. Decreased a little bit, but probably not at a constant rate. But at time 20, I know we were at 104, and we're able to decrease the height evenly from there. So let's see. So far we've got the height would equal 110, or 104, sorry. And then it's going to go down from there. Down by 0.75 meters per second. So 0.75 times something. How do I figure out how many seconds have elapsed? Well, what variable or what expression is that looking for? How many seconds have elapsed? Yeah, delta x. I need to know delta x. And what I have here is a specific value of x, 45.31 seconds since the ceremony began. But how many of those seconds has the flag actually been decreasing in height at a nice constant rate? 25. Yeah, 25.31. how much is this past the point in time when we were able to do this nice and smoothly? Y final, or x final minus x initial, change in x. So yeah, 25.31 seconds. And let me just drop this in here, 25.31. But that's just our delta x, 45.31 minus 20. And if we do this computation, we'll figure out the height of the flag that we need. I said you don't have to do it all abstractly. You can certainly grab a calculator and compute, all right, how much did it go down, and then where did it start, and think your way through it. Don't think of this as formulas to memorize, but when you're working with constant rate of change, it is the same relationships every time. It's just a matter of what specifics does the problem have that make one problem different from another a little bit. But when we're talking about change that happens at a constant rate, we have these relationships we can always use. All right, so I hope that was a little bit helpful in terms of how to write stuff out. What I want to take a look at, let's see, beyond that. So our other topics beyond constant rate of change that were the most recent ones at the end of Unit 2 were about distance and absolute value, which those are closely related topics in some senses. Let me open up this. So distance form here, actually, let me just go back to the beginning so I can click on something. I'll just show you use these PowerPoints so we can see this. So the distance formula, and let me make this bigger. Distance formula is essentially Pythagorean theorem. If you want to know the distance between any 2 points in a coordinate plane, you can find the delta x and the delta y that change horizontally and vertically if you're drawing it out in order to find the distance between them using Pythagorean theorem, hypotenuse or straight line distance between the 2 points. And I don't know if you looked at these examples. This is also in the textbook in section 2.6 about the distance formula. But if you wanted to know, is your house close enough to this cell tower to get good reception, and you know, like the 3.5 miles away is kind of the boundary of like where you're going to be really annoyed that everything's loading slowly. If you have measurements in city streets, we've got, apparently these units are 1 mile apart. So this is actually, normally it was something like 20th Avenue and 21st Avenue are 1/10 of a mile apart, but we'll go with these as being 1 mile apart based on this description. So if each of these units is 1 mile between B Street and C Street and D Street, and between 20th Ave, 21st, 22nd, 23rd, if I want to know the straight line distance between these, it's a matter of Pythagorean theorem. And here, we can see here with these nice whole numbers, I can just count the squares, 2 miles this way, 3 miles that way, find the straight line distance, and it's going to be slightly more than your 3.5 miles. Let me just, Pythagorean theorem says it's 3.6 miles. You're right on the boundary of like okay reception and not good reception. So if that's your deciding value on buying a house, then in this case, like, nah, let me look someplace closer to a cell tower. But in any case, you could determine the distance from another location if you have a coordinate grid or a measurement system set up that's in a grid to measure by. So let's see. Moving on to just looking in a grid, let's say that this point, a cell tower is at the location -2, 4 on this point. So whatever, 2 miles west of Central Avenue, 4 miles north of, I don't know, McDowell or whatever's going to be the Washington Street, I think, downtown. So wherever this is, we've got this location that's mapped out, and we've assigned it a coordinate position of -2, 4. If I talk about everything that's within 3 miles, so I I could easily see like 3 miles to the east, 3 miles to the west, north and south following the coordinate grids. But I could go 3 miles on diagonals also, and if I do that, it forms a circular boundary. So this is a circle with a radius of 3. And maybe in a geometry class or an algebra 2 class, you talked about formulas for how to write a formula for a circle or an equation for a circle, and probably at the same time like parabolas and hyperbolas and lots of ellipses and all sorts of fun things like that. If that sounds like oh, I remember that unit, that was awful. I'm not going to ask you for what's the focus of the parabola or anything like that, but just circles, distance formula. The formula for creating a circle or an equation that describes a circle is just based on distance formula. So I want to describe all the points x, y that have a distance of, in this case, 3 units from that point. Well, regardless of what direction I point them in, if I want to know, well, how far is the what's the left to right distance between this center point and some xy point on the circle? And it doesn't matter if it's like straight across or some weird diagonal. If I want to know left to right, how far is it? I'm like, well, I would like to know which one's larger, but if I don't, it won't matter in the end. I'm going to do some squaring. But if I want to know the distance between this point here, xy, and that center point, well, I take the point x and the point -2, and I subtract them to figure out how far away they are. So I'll just say x minus -2. And I can do the same with the y's. How far is a y value here from that? Oh, maybe it's 4 minus y, or y minus 4. Because what I really want to know is straight line distance, so hypotenuse distance, or hypotenuse length, I should say. So if I take a squared plus b squared, take the square root, our distance formula should tell me the distance. Now I want it to be 3 as that distance. So a squared plus b squared equals c squared. And it doesn't really matter. Here, let me skip on to something else. Here, xy, any point. It doesn't really matter which is larger, x or -2, y versus 4, because in terms of Pythagorean theorem, I'm going to end up doing that subtraction and then squaring. And the squaring takes any negative out of the picture, so it doesn't really matter what order you subtract in. But if I do x minus -2 squared and y minus 4 squared, and then take the square root, which, as some of you found in one of the questions, there wasn't that little arrow on the answer to be able to give you the square root sign. In iMath, you can type to do a square root of, I'm just going to use 17 as an example rather than writing out a whole long expression. If I want to type this, there's like 3 ways you could do it. The maybe most useful way to write this, you could type SQRT. And if you type in something like this and do preview, you'll see it has square root of 17 with the radical symbol over top. But you can also use exponents. Remember, a square root's the same as a 1/2 power. So you could just do 17 to the power, well, 1/2, which you need to put in parentheses. Or if you don't want to deal with parentheses, use a 0.5. 17 to the power 0.5. And you don't have to have the leading 0. I just put it there because decimals are hard to see from a distance. But in terms of if you want to type in a square root of whether it's just a single number or a whole expression, put it in parentheses. So if 17 weren't just a 17, if it were like a whole expression, I'd want to, like if there's x minus 4 that I want a square root of. In parentheses, to the 1/2 power or the 0.5 power, or square root of SQRT, parentheses, and that'll give you a square root symbol if that little math palette isn't coming up. Let's see. Oh, so just in terms of this circle centered at -2, 4. And you can have this simplified other ways. It's like I said, it doesn't really matter what order you do these subtractions in. So it might look a little different from one person to the other, but they'd be mathematically equivalent. x minus the x coordinate of the center squared, and y minus the y coordinate of the center squared. That's your delta x and your delta y squared. Set it equal to your radius squared, or have a radius equal the square root of all of that. Now, if you want a whole circle, you'd need a plus or minus square root there, or you could just leave it unsquare rooted, like leave it in a squared plus b squared equals c squared, like don't take a square root, and then you have the expression for the whole circle. So, like I said, distance formula, I think once, other than the square root issue and a couple of concerns about what order you're supposed to subtract in, looks like you did a good job on the lessons for that. Just be careful with negative signs, I guess. Don't forget them entirely. But there is lots of squaring involved, so the order of subtraction isn't most important. Now, absolute value stuff is a little bit trickier. So absolute value inequalities are one of those things that I know, I used to teach high school. I know it's just one of those things that you run across for a couple of weeks sometimes, and it's just weird. It's like, you have to remember a whole bunch of different stuff. It's absolute value is about distance, trying to measure about how far apart things are, but not worrying about the positive or negativeness of it. That's a lot of the time what absolute values are used for. We take absolute values so we find how far apart things are, or find a distance between things without concern for direction, or to find a speed without worrying about whether it was north or south or something like that. So these absolute values are just so you have the size of a number without worrying about whether it's positive or negative. So lots of times they're used for describing things where I just know that the distance needs to be a certain amount or larger, or the distance needs to be this one certain amount or less. So those absolute value inequalities are a quick way to describe kind of bounded situations like that. But sometimes it's easier to understand if you translate that back into something that doesn't have an absolute value symbol in it. So, as an example of an absolute value situation, kind of common use is this tolerance, or an acceptable difference, an acceptable distance between two things. In this case, the carpenter needs to cut a wooden board to a length of 7.6 inches. There's a tolerance of 0.1 inch, meaning you're trying to cut wood. You hope that's exactly the size that you want, but just due to the size of the blades and cutting stuff, it's probably going to vary a little bit from one piece to the next, and just your eyesight ability to line things up precisely and how tightly you press things against guards. It's going to vary a little bit, but we can't have it vary by more than 1/10 of an inch, or else it's not going to fit into whatever we're trying to use our piece for. So just from this description, if I need to try to cut something to be 7.6 inches long, and it can vary from that ideal by up to 1/10 of an inch, 0.1 inch, there's an acceptable range of numbers. It could be a little bit larger or a little bit smaller by that 0.1 inch. Either of those is okay, but this tolerance expression gives us kind of a range. It gives us a center point and a little distance on either side of that center that's okay, that's within our acceptable range. So, some certain examples of things that fit within this range here. 7.6 inches is the ideal or the goal. I could be a little bit smaller or a little bit larger, so 7.55, 7.68, 7.61, those are all fine. Boards that came out to be that length would be usable. Things like 7.72, not so good. That's a little bit too long. Or 7.49, a little bit too short. There'd be too much of a gap when we try to construct this. So we have a range of acceptable numbers that would be ideally exactly 7.6. Are we going to be able to get exact all the time? No, but as long as we're within a certain range, and if you can see this, thinking about the distance that we were just talking about in circles, here's the center of our circle, going one way or the other way, just thinking about like a one-dimensional distance instead of circles, like a distance measured in 2 dimensions. We have this range. We can go to the left or the right, by up to 0.1 inch, 0.1 unit, and still be okay. So this graph here is a demonstration of the values that make this absolute value description true. Now just to quickly get to, I don't see an absolute value in this. Absolute value is a distance. And let's see, without absolute values, I could say this is the range of numbers that's okay. 7.5 through 7.7 inclusive, up to and including, down to and including those endpoints. But I could also talk about, let's see, where is this? Just listing the difference between my board length and our goal. Say this is our error, the distance that's acceptable, or the error that's acceptable in this case. By subtracting, put the absolute values, because I don't care whether it's bigger or smaller, it could be either. So subtract and just make it positive. And say I want that error to be less than or equal to 0.1, or that difference from the ideal, the delta x, to be less than or equal to a certain value. And that's what these absolute value inequalities are representing. You can think of that expression inside the absolute value signs as something that represents an error or a distance from the ideal, or distance from the center, the goal. And then the number by itself, that's on the other side of the inequality, as how much that error is allowed to be, or how much that distance is allowed to be. Now this is a less than. If it was greater than, I'd say I want to be at least this far away from the center. I don't want to be less than 2 miles from this electrical plant. So I can go down the street more than 2 miles this way or more than 2 miles that way. But the distance you measure by subtracting. Delta x, take the two x values or the two whatever values they are and subtract to get that difference or delta. All right, I will see you on Thursday. I apologize for talking a lot, but I want to make sure we're kind of regrouped and back on this.